We're gonna get started here in a second. All right, I think I'm going to go ahead and get started. So let me share my screen with you. All right, so we need to finish up worksheet 1 today. And so that was shared with you already, so you should have that. That was from last week. And we have done many of the problems in there already, but the ones we haven't done, actually we've done a couple of the problems, I should say, in there already, but we haven't done them all. Let's see, the last one we done was number 3. And if you remember, what we were looking at on worksheet 1 from last week was we saw that the derivative of a momentum time graph gave you force, and the integral of a force time graph gave you the change of momentum, the impulse. So we are going to be whiteboarding worksheet 4. And for worksheet 4, I just copied from mine. It's not on yours, or what did I say, worksheet 4? Excuse me, problem number 4 on worksheet 1. I went ahead and copied kind of a picture of somebody throwing this baseball so you can kind of imagine what's going on. And what I need to review with you is that there are 2 ways that you can find the change in momentum. You can either find the impulse, which again is the area of a force time graph, or you could figure out what the impulse or the change of momentum is by doing mass times final velocity minus mass times initial velocity. It just depends upon what you know, okay? So we're going to be whiteboarding problem number 4. And so I'm going to be putting you here in rooms in just a second. Let's see. Looks like some of your partners haven't come, so I'm going to probably be pairing up some of you with different partners. Sorry, but a lot of your partners are here, so let me go ahead and open up the rooms. So, yeah, there you go. Jaden, you should have got an invitation. If you can please click on it and go in the breakout room with your partner. And Kyler, I think you have an invitation too. Any questions?
No, we're good.
Thank you. I don't think so.
Okay.
Yeah.
Any questions?
Hey, Mr. Limfesti.
Hey.
No, I think we're good.
I don't think we have any.
Okay. Any questions?
No, I don't think so.
Okay.
Oh,
Okay, so does anybody would like to share with their whiteboard with the group? Feel free to go ahead and do that at the very bottom of the screen. There's a share screen, little green button, pop up, will come up, and then click the blue, share the screen. We're trying to figure out what's the change of momentum of the ball. Got 90 minutes. We can be here all day.
All right, I'll pull it up.
Oh, awesome.
Just give me a second.
thanks,
You
Dan.
don't mind. I just gotta get to it. You said number 4, right?
Yep.
Alrighty. Okay. Is it? Where's the share screen? Oh, there it is. Alrighty. Wow. And then number 4. I think this is number 4. Hope it is. Oh, that's number 3. Oops. Which one is number 4? I don't.
It doesn't have a picture with it. It's
Was it the? Oh wait, I
it's
think
the baseball player one.
Is it baseball player?
Mhm.
Hold on. Oops. Okay. Sorry. This one. Okay. Got it. Yeah, number 4. Okay. So I did P is equal to MV. Or actually, I ended up doing something else. I did F net is equal to delta P over delta T. I actually did mass times velocity. Oops. Yeah, because you see on the top right, I said F net is equal to delta P over delta T, which is also equal to M times delta V over delta T.
Okay. So where's your answer at? I'm
The very
confused.
bottom, it's the 5.94.
Ah, gotcha. Okay. So that seemed kind of circular. So how did you get that answer? Oh, you got it by taking 0.14 times 42.42. Is that it?
Well, I did 132 times 4.5 times 10 to the negative second,
Oh,
and then
does
divide
that
that
give you?
by.
Okay.
Well, that
Does
gave
it?
me delta V, and then to find what P was, I took the mass, which is 0.14 times the velocity.
Seems like you're chasing your tail a little bit. Wouldn't just force times the time give you the change in momentum?
Force times the time.
Yeah, so the 132 times 4.5 times 10 to the negative second, wouldn't that just give you the 5.94? So it seems like you figured that out, and then you found the change in velocity, and then you multiplied that by, and then you went backwards again. You multiplied by 0.14 and got the same answer again. Do you have a calculator there?
Yeah, I do.
Take 132 times 4.5 times 10 to the negative second. What do you get?
Oh yeah, I did get the same thing.
Yeah, so I think you
I
worked
guess I just
harder.
overthought it then.
Yeah, I think you worked harder than you needed to. Yeah. All right, so can everybody give Dan a hand there? Thank you at the very bottom. Yay. The reaction. Yay. Okay. All right, so could you guys go ahead and get in your groups again and do the next problem, number 5, please?
How tay.
Is the big group?
Indeed.
Hey guys.
Shalom.
Hey Henry.
Hey.
Been listening to any good music lately?
A little bit of King Gizzard and the Lizard Wizard.
Nice. I'll have to go
Yeah.
check that out.
You
What
better.
was it called again?
King Gizzard and the Lizard Wizard.
Oh, here it is.
Are you talking about your music again, Henry?
Yeah. Bryant
Is your,
asked.
is your favorite song Planet B?
No, but it's a good one.
Yeah. What about People Vultures?
That's pretty good. Pretty good.
Okay, I need to get a picture for attendance. So if you can kind of turn on your camera, at least so I can see thumbs up or something. So on count of three, I'm going to be taking a picture. So again, make sure your camera is turned on. All right, so 1, 2, 3. All right, let me save that. Okay, all right, thank you. All right, so does somebody want to share their problem with us, their whiteboard? And we got all 90 minutes. If who's that?
Annie, I can
Oh,
share
perfect.
mine.
Yeah, go ahead. All right, and just walk us through how you solved it then.
We used the change in momentum equals mvf minus mvi, and then we plugged in the momentum from the last problem and the mass.
Okay, and you got about 42.4 meters per second. I was a little curious because I want to know what speed that was in miles per hour, because it's kind of hard to imagine. Although 42.4 meters in 1 second, that's pretty far. So that's about 95 miles per hour. So that seems about right. Everybody give Annie a hand. Nice, yay. Thanks. Okay, so now we're going to go ahead and start whiteboarding the next problem. I believe it's number 6. So it's the same, it's a continuation of the last problem. So the ball still have the same mass of 140 grams. So I'm going to go ahead and open up the rooms for you.
odd that you seem to be the only person with this problem. Maybe you're the problem.
Did you actually send that to her?
Swear to God.
Oh
you guys
my
doing?
god.
What you guys doing?
Good.
Oh, hey.
What are you doing?
Oh,
Huh?
we already solved it.
Yeah. Did you see my note to you?
Incorrect.
There you go. Work on it.
Okay.
Hey, Krishna. I was looking at the problem you guys are working on. I don't think, Krishna, can you hear me?
Yeah.
I don't think something's not right there. You have a final velocity of 85 meters per second. I don't think that's right. Something's not right. 1320. Oh, I know what the problem is. You have the initial velocity as being 0. That's not true. Remember, you just found out the initial velocity. Remember, the ball is coming toward, from the pitcher, it's coming toward the person at 42 meters per second or whatever that was in the last problem,
Oh, okay.
right?
Yeah. I forgot. Never mind.
Okay, so let's see. Okay, and then there's another problem there. If you think about the initial velocity and the final velocity in opposite directions, so one of them's got to be negative, and since you have VF as being positive, that VI's got to be negative. So that negative, so it should be minus a negative 42.3. So it's going to be end up being VF plus 42 point whatever. Does that make sense?
Yeah.
Go ahead and give that a try. Okay.
Okay.
So are you guys still stuck? You did see,
We're just running through it real quick, just to
So-
make sure.
so I'm looking at your picture here, and I can see what the problem is. Do you see you have your initial velocity of 0? You've got over on the right-hand side of the picture, you got negative, what is it? Negative 1320.
1320.
Yeah, times something equals 0.14 times quantity VF minus 0. Well, that's not true. This is not T-ball. Remember, the ball was coming in, the previous problem was coming at the batter at like 42 point something meters per second.
Oh,
And so
so do we?
here's the problem. The VF and the VI are in opposite directions. So if you're going to make the VF positive, which is fine. Well, actually, wait a second. Okay, there's a couple problems here. So if you're going to have the VF positive, which is fine, then that VI needs to be negative. So it's going to be minus a negative 42 point whatever. So it's end up being VF plus 42. The other problem is
Okay.
this. The other problem is this. If your VF is positive, then that means on the other side of the equation that where you have the negative 1320 or whatever, that needs to be a positive 1320
Okay.
because you have the VF is positive. Because the VF would
That
be,
makes sense.
yeah, does that make sense? Okay, so the VF is in the
Yeah.
same direction as the force. So it's 1320 times 9 times 10 to the negative third. Equals 0.14 times VF. And then it's going to be, or it's times the quantity, sorry, times the quantity VF. And then it's going to be minus a negative or plus 42 point whatever. And then you can solve it. Okay. All right.
Oh, cool. Thank
All
you.
right, thanks.
Yep.
Okay, I forgot about the initial velocity.
Yeah.
Okay, somebody want to share this problem with us?
Oh.
I can share.
Okay, thank you very much, Daniel.
So this is what we have here.
Okay, so walk us through there. So you know the initial momentum is 5.94. That was from the previous problem. Okay, and then, so walk us through how you figured this out.
So we have J here, and then we multiplied it by the amount of time, which is equal to this part here.
Okay, so that would be the impulse on the ball. Got it? Okay, that makes sense. Okay.
So we have the this number we had from the last equation minus the impulse, which gives us that.
Okay.
And then we multiplied that times the mass of the ball, which is where we got that.
Oh, you divided. Okay, so
Divided it, yeah.
So basically, it's the same speed, but in the opposite direction. So in a way, it's kind of like this baseball is being bounced back. So it's coming in at 42.4 meters per second, and it's going out at 42.4 meters per second, which gives us this huge impulse of 11.88 kilograms times meters per second. Okay, looks great. Give Daniel a hand, everybody down at the bottom. Yay, awesome. Okay. So now we're getting ready to do the next one. So let me share with you my screen. I think the next one, oops, sorry about that. I think the next one is this still a continuation? Oh, actually, I want to do this one together. Number 7, it's a conceptual question. So if you can turn on your mic here. So in number 6, we just figured that answer out. It wants to know in number 7, what force does the ball exert on the bat? In number 6, we know the force the bat exerts on the ball is 1320 newtons. What force would the ball then exert on the bat, excuse me. So what'd you guys say?
13,
Isn't it just 1320?
Yeah, it's 1320, just in the opposite direction. Right, that's just Newton's third law. Good. All right, so we're done with that one. And now we're gonna move on to number 8, which this is a totally different problem. It's not a continuation. In this one, you need to draw a force diagram. That's gonna be important to help you solve this last part. So make sure you draw the force diagram first, okay? So let me stop sharing and you guys go ahead and go in your breakout rooms. Hi, Emily, I want to talk about your problem. So your force diagram looks great. Okay, that looks great. But I have a couple questions for you. Let's see. Are you guys able to hear me, first of all?
Yeah.
Okay, so I'm looking at your calculation there. You have 860 times the 4.36 times 10 to the 4th is the delta P. So I think what that is would be, since the initial momentum would be 0, that's the velocity times the mass, right? But be careful there. Is that really the mass?
No, it's e to the 5th.
Right. Actually, it'd be e to the 3rd because you have to divide by 10, right?
Oh, yeah.
Divide by 10, yeah. So it's actually e to the 3rd. Oh, no, not the 860. The 860 is fine.
Oh, okay.
It's just where you have e to the fourth there, it should be e to the third. So 4.36 e to the third. Yeah, there you go.
Yep, I was just making sure because I just realized now it said the engine provides an upward force of 8.90 times 10 to the fifth. Then
Okay, so that's the second thing I want to talk
Yeah.
about. So could you look at the second to the last step where you have 8.9 times 10 to the fifth t? My question is, in that equation where you have force times time, which force is it? Is it the weight force? Is it the thrust force? Or is it some other force?
it's probably the thrust minus the weight then.
There you go. It's the net force.
Oh,
So that force isn't right. So go ahead and do the calculation again. Okay. See ya.
Thank you.
Yep.
Just to as a study.
Yeah.
Hey, I have a question about your whiteboard, guys. Can you guys, you can hear me okay?
Yeah.
Great.
Okay. You're using the equation force times time equals mvf minus mvi, right?
Uh-huh.
Yeah.
Okay. Where the initial velocity, because it's a rocket, would be taken off would be 0. I totally get that. But I want you to look at your equation there. You got 4.36 times 10 to the fourth. Is that really the mass?
Oh.
Oh,
Yeah.
wait. You have to do
Divide by 9.8.
Yeah.
Yeah, so it's going to be really 10 to the third. Oh, is this? Oh, I thought this was the other Luke. I can't tell when you don't put your last name.
Oh,
up.
yeah. I can't figure out how to change it.
Sorry, but that's all right. Keep on working in this group. There's one more problem I need to talk about with you.
Alright.
So you see that problem now. So that should be 10 to the third. The other problem is this. When you have the force times the time there, if you look at your force diagram,
Mm-hmm.
what force is that?
The force down or up?
Well, that's the question I'm asking. So in the equation force times time equals mvf minus mvi, what force do you plug in for the F times T?
The force upward.
Upward.
Okay, so are you saying there's no other force acting on this rocket that's going to cause a change in momentum?
The gravitational force. So do you have
Right.
to subtract?
Yes, it's going to be subtracted. It's really the net force. Okay.
Okay.
So why don't you make that fix, okay?
Alright.
Okay. Hey, Krishna, can you hear me?
Yeah.
Okay, I have some questions about your whiteboard. Okay, so I see that you have an answer of, well, actually, you have two answers. Which one is it? Is it the 42 or the 4.2? Or you're not sure?
That's Luke Royer. He's not in
Oh,
my group.
gotcha. Okay, so it's not the 42. You're like, it's the 4.3 about, right?
Yeah.
Okay, so I totally agree with the right-hand side where you figure out the mass times the 860 minus 0. Get that. But look on the left-hand side where you have force times time. If you look at your force diagram above there, you just plugged in the thrust. Is that the only force acting on the rocket?
No.
No, so you really need to use the net force. So it's not going to be the 8.9 times 10 to the fifth, it's going to be the net force, okay?
Yeah.
Okay, so you go ahead and fix that then, all right?
Okay.
Can you guys hear me?
Yes.
Yeah.
Okay, I have a couple questions to ask you about your work, okay? So
All right.
are you guys looking at it?
Yeah.
Okay, so I totally agree with the equation FT equals MVF minus MVI, okay? But I want you to look on the right-hand side. Look at the number you plugged in for the mass. Is that really the mass?
Oh, no, because it's in newtons, not kilograms.
Right, so you have,
Divide by 10.
right, so it's gonna be 10 to the third,
Okay.
okay? And then I
Thank
have
you.
one, so that's one problem. There's one more problem.
All right.
So if you look at the left-hand side, you plugged in for the force, the thrust. But I want you to look at the force diagram. Is the thrust the only force acting on the rocket that causes a change in momentum?
Oh,
No. So how would you figure out what force to plug in there? What do you have to do?
Would be-
You have to subtract the
Yeah.
weight.
So yeah. So once you just forget about the drag and just find the net force with those two forces, okay? And then
Okay.
fix it.
Right.
All right.
Thanks.
See ya.
I don't know.
Hey, John
It's kind
Caleb.
of confusing.
John Caleb, can you guys hear me?
Yeah.
Okay. So are you guys still looking at your whiteboard? Because I want to talk about it a little bit.
Yes.
Okay, so you're using,
Okay.
I think you're using the equation force times time equals momentum, change in momentum, right? Yes?
Uh,
Yeah,
yeah.
so I totally agree with the left-hand side. You did a good job where you have the mass times 860. I totally agree with that. The only problem I have is on the right-hand side. The only force you plugged in was the thrust, but look at your force diagram. Is that the only force that acts on the rocket that might change its momentum?
No.
No. So really,
I know there's gravity too.
yeah. So you really have to plug in the net force. Okay.
Okay.
Okay. All right. I'll let you fix that then.
Okay.
Hey, Jaden, Henry, can you guys hear me?
Yeah, Jaden just went to go get something though.
Okay. So Henry, are you looking at your whiteboard?
Yeah.
Okay, because I want to talk about it a little bit. So
Okay.
you use the impulse, force times time, is equal to the change of momentum, where the initial momentum is 0. So I totally
Yeah.
agree with your logic. Also, I agree with your left-hand side. You did a great job there figuring out what the mass times the velocity is. The problem I have is on the right-hand side. Can you see you plugged in for the force 8.9 times 10 to the fifth? Well,
Yeah.
that would be the thrust, but oh, I see part of the problem. You didn't draw a force diagram. There's actually two forces actually you did have a force diagram. I see it now on the picture. There's two forces that act on the rocket, not just one. So how would you figure out what the force is that you plug into that equation?
Would it be the difference between the forces?
Yeah, so you need to recalculate there. It's going to be different, okay? All right,
Okay.
see ya.
See ya.
Yep.
Oh.
Slacking.
Oh, there he is.
Hey, guys.
I bet
Sorry,
oh,
it
hey.
took. I'm going around. There's lots of mistakes that I have to fix. Okay, so
Was it Krishna?
no, it's pretty much everybody. So you're on my list now. Okay.
Uh-oh.
Oh.
Are you guys looking at the whiteboard?
Yeah.
Okay.
Yeah.
Yeah, Brian has it up, I think.
Okay, so I totally agree with the force diagram. Looks great. I also agree with the idea of using impulse equals change of momentum. Okay, the problem I have is look on the right-hand side of the equation. Look what you plugged in for the mass. Is that really the mass?
Oh, it's in newtons.
Yeah, you have to divide by 10, right, to figure out the mass?
Yeah.
Okay,
You're
that's one problem, but there's one more problem.
Oh.
If you look on the left-hand side of the equation, you have 8.9 times 10 to the fifth. Well, that's just the thrust. Look at your force diagram. Is that the only force acting on the rocket?
Oh, we have to do F net.
Yeah, you have to plug in the net force into that.
Oh, so would that just be 8.9 minus 4.36?
Yeah, you plug that in for the where you have 8.9 times 10 to the fifth. You have to subtract them there.
Gotcha.
All
Okay.
right, so I'll let you guys work on that. Fix that, okay?
Thanks.
Yep. Hey guys, can you hear me?
Yep.
Okay, so are you guys looking at your whiteboard? Because I want to talk about it a little bit.
Okay.
All right. So I like your force diagram. Excellent force diagram. In fact, I think that's the best force diagram I've seen all day. That's awesome. I like the picture. And your equation where you have force times time equals change of momentum, MVF minus MVI. That's great. But I have a couple problems. Can you look on the right-hand side of your equation? Look what you plugged in for the mass. Is that really the mass?
Oh, it's supposed to be
10 to the third, right? Yeah.
E3.
Okay, and that's one problem. And there's one more problem. On the left-hand side of the equation, for the force, you plugged in 8.9 times 10 to the fifth. But look at your force diagram. Is the thrust the only force acting on the rocket?
Oh.
So how would you figure out the force that you should plug in there?
Oh, that would be F net then.
Yeah,
You have
so
to
yeah,
find
figure
F
out what the
net.
net force is and plug it in. All right, good. You guys go ahead and fix that, all right? Okay, so could somebody share with us their whiteboard? And we're kind of going long on time, so quickly, somebody share.
I got it.
All right, thanks. And just kind of
Cool. See
take
that?
us, yeah, we can see it. So go ahead and take us through
Okay,
how
cool.
you went about solving it.
So I just used the FT equals MVF minus VI.
Good.
So we plugged in 8.9 times 10 to the fifth minus 4.36 because that's the net force.
Good.
And then we let t as its own variable. And then we did 4.36 divided by 10 because it gives us the weight in newtons. So we have to divide it by 10. And then there's no initial speed. So VF just equals 860. And we got 4.43.
Nice. And by the way, if anybody used, I think 9.81, I think you get 4.5. So can everybody give Brian a hand there? Thank you. Or Brian, yay, awesome. Yay. Okay, so let me share my screen with you now, since we're going a little long on time. Okay, so I'm going to have you finish the worksheet 1 by yourself. There's only one more problem, so we can quickly whiteboard it. So please make sure you're collaborating on that. I also need you to do a lab to get the data for it, and so I want to spend some time going over that really quickly. If you click on this, it will download directions, and you can follow those directions. It's pretty well laid out pretty well, but I actually want to show you some problems that you might run into. First of all, when you go to the site here and you click to start it, it won't work because it's Java, and Java doesn't play nice in Chrome. So let me go back. What you have to do is copy this URL, and you have to open up Firefox, Mozilla Firefox. And I'm going to paste it in. By the way, this is all written down in those directions that I showed you a second ago. And now when you click on play, it'll look like it doesn't work, but go ahead and click again and just say allow, and then it totally works. And what you're going to do is you're trying to figure out what the relationship is between the initial system momentum and the final system momentum. And again, this is written down on the directions. You're going to check center of mass, momenta diagram, and kinetic energy. You're also going to click more data. As far as getting data for this, it won't take very long, maybe 15 minutes to get the data. So you can move this wherever you want. You can change its velocity to be whatever you want. You can also give this one a velocity, whatever you want. And I'd like you to get like 6 different, of course, 6 data points, but 6 different types of collisions. So for instance, you can have it where one of them's just simply sitting still, colliding, right? You could do something like maybe one's catching up with the other one, kind of colliding like that, right? Or let me reset. Maybe you have them coming toward one another, colliding. Lots of different collisions. But I also want you to try different types of collisions that wait a second, where'd my sheet go? Right down here, I want you to try at least 2 different what's called elastic collisions, 2 different perfect inelastic collisions, and at least 2 inelastic, just simply inelastic collisions. So the second one here and the third one is kind of confusing because it says perfectly inelastic and the last one just says inelastic. So I kind of want to show you the difference between those and how you get those. Well, there's a little slider here. You can slide this thing to be, if it lets you. You can slide this wherever you want. I'd like you to slide it over and do completely, I should say, elastic collisions. Okay. If you slide it all the way in the opposite direction, this is what's called a perfectly inelastic collision. It doesn't say that there, but it's perfectly inelastic. And then in between, anywhere in between, doesn't matter where, is just simply called inelastic. So let me go over that again. I want you to do at least 2 elastic collisions, any type, any direction, could go however you want. Do 2 that are just simply inelastic collisions. Again, any type you want, however fast, whatever. You can change the mass even. And then I would like you to do at least 2 perfectly inelastic collisions. And again, you can have it go in different directions. Notice I'm not defining what these words mean. In fact, that's kind of part of the lab. As far as getting data, let me explain what you're doing for getting data here. You want to figure out what the initial system of the momentum is. That means the total momentum of both the red and the green. Well, it gives that to you right down here. Hopefully you can see my cursor. The red is 1.49 and the green is -0.67. And then after they collide, it will also give you the total, or the two momenta. You just have to add them together. So you figure out the total momentum before, total momentum after, and that you only need 6 data points. Okay, I want to go back to those directions though, because there's more to it than the 6 data points, because I don't think it'll take long to get those data points. The other part is number 5 here. I've given you some I've given you some new words, which I don't like to give you new words. Those words are elastic, perfectly inelastic, and just simply inelastic. Well, part of the lab is trying to figure out what those words mean. So in other words, when you do the lab, you're going to see that when you do an elastic collision, it looks sort of different than an perfectly inelastic collision. Okay, and so you'll see something happen. You'll get some observations. So you'll be able to answer A and B there. I also want you to look at this momentum chart down here. This is kind of a conceptual tool. So you're going to try to figure out how that works. And then also, let me go back to this. This little X here for the center of mass. When you're doing collisions, I kind of want you to watch that X too. That's where the center of mass is, and I want you to see what happens to that as well. Okay. So what I'm kind of hoping that you'll do for this lab is that maybe you'll create your own Zoom with your lab partners, and you'll actually just simply get the data that way together. Okay. You don't have to do this response sheet or anything. Don't feel like you have to do the response sheet. Nope. All you need to do is get the data and kind of be able to answer those questions down here for number 5. And please have your graphical and mathematical models ready. All right, let me go back to this and we're almost done. The attendance quiz. This is the last thing you have to do for today. And I've got some good news. The 4 people who presented, your reward for presenting is you don't have to do this attendance quiz. You can if you want for bonus. It won't be a lot of bonus. It's only 4 questions. It's very similar to what we just did in whiteboarding. Anyway, the access code is lowercase k, number 5, lowercase r, lowercase t, capital D, P, lowercase p, up, lowercase f, 9, and lowercase z. So again, Dan, Annie, Daniel, and Bryant, you don't have to do this if you don't want to. But if you want to get bonus, you can do it. All right, let me stop sharing.
Could you give the code again?
Oh, sorry. Yep. It's lowercase k, 5, lowercase r, lowercase t, uppercase D, lowercase p, lowercase f, 9, lowercase z.
Thank you.
Yep. Oh, I have to get a picture before you guys leave. One last picture. So if you could turn on your cameras and count of 3. 1, 2, 3. Okay, that's it. See you guys later. Bye.
Cool. Thank you.